This is the video for the random walk routines. Here on the left is one of the routines, and here on the right is the second routine. We'll start with the one on the left. Set small to 1, divide it by 1,000. Set return value to 25, divide it by 100. We're actually not going to use that, but I went over it anyway. Fill 121 values at matrix with 0. Well, this is where we're going to build our matrix down here. It's going to be 11 by 11. 11 times 11 means it has 121 values, and here it says we're setting them all to 0. It's a null matrix. Then we're going to set A to the game number, multiply A by 5, and then add to it 5,000. Then we're going to divide that by 10,000. So now we're going to have a value around 1/2, 0.5. Then we set B equal 1, and we subtract A from it. That means the sum of A and B is 1. Well, that can be used in a matrix for transitions. Well, let's go next. It sets J to 11, then for I of 2, and down here we have I goes to 10. We can say this is the rows, row 2 to row 10. It's going to skip the first row, and it's not going to go to the last row. It says set matrix plus J to A. Well, it said offset 11 is the first value of J. Well, there's 11 in a row, so the first one is this one here, where it says 0.502. Then it says set matrix plus 2J to the value of B. Well, 1 away from J, 2 away from J, this is this one here, 0.498. This is going to be a transition matrix. Let's see what happens next. It adds to J 12. Well, 11 would put it to the very next position on the next row. 12 would put it over 1. Oh, so they're all going to slant with the diagonal. There's going to be a value to the left of the diagonal, a value to the right of diagonal. Well, the one on the left is the probability of going up one row. In this case, call that up. And the other probability is going down. And it's doing that for every single one from row 2 down to row 10. Now we'll continue on with it. Once it does those rows, then it says set the value at matrix to 1. Well, that's offset 0, so that's this one here. And then it says set the value at matrix plus 120 to 1. Well, that's the one at the very end. So now we have a completed transition matrix. All the rows add up to 1. Now let's look at the other routine. It sets the control register L to 11, register M to 11, and register N to 11. Well, L is used to tell it the offset to the next row. M tells it how many columns there are. Well, now the rows and columns are the same, meaning there's no extra values in the 121 values we talked about. All of them are used by the matrix. If the offset L would be greater, then there would be some values in our matrix that would be 0 all the time and never used. But here it is, rows and columns 11, 11. Then the position XY is being set. That's where it's going to show the matrix. And then here it is, box N, box the numbers 123,000 added to the number of positions, and the positions here it says is 5. That 123,000 indicates that it must use these values to display the matrix down here. So it says here 5 positions. Well, 3 positions for the significant positions of the number, 1 position here for the sign. This is blank, so it's positive. If there was a minus sign there between the 2 and the C, it would be a negative number, but this is a transition matrix. None of them are negative. And the next value here is a lowercase c, which indicates 3 decimal places. That's why this is 0.502. All right, we'll continue back over here. We now shown that it displays it on the screen at this XY position. Then it moves the 121 values in our matrix to another list called hold matrix. Then it sets the control register N to 1011, not just 11 as it was set up here, but 1011. That indicates that it's a square matrix, 11 by 11. It no longer cares what MS said that it was 11. It says, well, it's square, so it's 11 by 11. It needs that for this instruction down here, multiply list. It's going to multiply a matrix by a matrix, giving a matrix as the answer. And here we go. It's going to go for I of 1, down here next I 8. It's going to go around here 8 times. Each time it goes around, it's going to do multiply list, whole matrix, time whole matrix, giving steady state matrix. And then the next line says, take all the values of steady state matrix and put them in the whole matrix. You say, well, why didn't it just say whole matrix time whole matrix to give you a whole matrix? Well, the reason is because when it's doing the math of multiplying one times the other, it's changing the values in whole matrix. Therefore, it's not going to get the right answer. So we have to do it this longer way. Put it in the steady state matrix, and then move the steady state matrix into whole matrix. Then it goes around again and squares the matrix again. It goes around 8 times. That means it's going to raise the power of the matrix to the 256th power, 2 to the 8th. That's going to be the matrix we're going to show down here. Well, then it says for I of 0, if the value in steady state at offset I is greater than small, go to BE. If it's not, set steady states of I to 0. And do that 121 times. It's going around every value that's in the steady state matrix, and that's this one down here, and checking to make sure that its values aren't below this small value that we developed up here, which was 1,000. And the reason it's doing that is because when it displays the matrix down here, and one of these values could be really, really small, and what happens then is it's still going to display it here. And it's going to look like, oh, there's values everywhere. But when you look at the exponent for it, it's like the letter Z, meaning it's really a terribly small value. So what we do is we just get rid of them. That makes it look a lot nicer. Here you can see at the steady state, there's only values in first column, and the last column. Now let's go see, well, we'll finish up with what else it does here. It adds 185 to Y. Well, this is at one position on the screen, and then this is going to be at another. And then it says set NS back to 11. Well, we needed these values up here. L and M are still 11, but NS have been changed, so it sends it back to 11. And then it boxes the steady state values onto the screen. Well, let's go down here and look at this. We see highlighted here is the middle one, which in our example here is going to be we have $5. We started out with $5. Now we're in the steady state, and it says 0.512 is the probability that we end up $0. And on the other end, it says a probability of 0.488 that we end up with $10. So it looks like you played the game 256 times and you didn't have much of a chance to get the higher value of money. Alright, this is the end of the video on random walk routines.